Hi, good afternoon, everybody. Thank you very much for coming along to the webinar this afternoon. We will give everybody else another moment or two in case people are running a couple of ticks late. I appreciate people might be just coming back off their lunch break. In case anyone is unaware, this is the fourth webinar in this series. So if you haven't caught the first three, you can go on our website and access the recordings of the previous three, if that is of interest. But as I say, we'll just give people a couple of ticks to join if they're running a little bit late from their lunch break. I think I'll just give people about 30 more seconds and we will get started. And hopefully people can catch up with things as they join if they are running a moment or two late. As I hope you've all probably figured out from the slide in front of you, I am Laura and this is my colleague Alex. You may have got that the wrong way around. It is very confusing. So I think we can probably go ahead and get started. Hopefully, if anyone is running late, they can just go ahead and join and hopefully figure out what's going on as we go along. So if we start off with a little bit of housekeeping, then as you've probably already noticed, you are on mute. If you have any questions, comments, queries, anything of that nature, you can just pop them in the chat and then we can see them and we'll get round to answering those for you. If we do have any queries that you bring in that we're not able to answer for you live on the webinar, perhaps they're just a little bit long and detailed, we just don't have time to get around to them all. Obviously, we do have your details from when you registered for the webinar, so we'll just be able to reach out to you afterwards with a bit more information. And as I just mentioned, this is number 4 in the series, so if you want to go back to our website, you can register for the first 3 on demand if you want to catch up. So obviously you're here to find out all about electronics reliability and the reason you might be interested in that and why it's important for small to medium-sized businesses. Obviously electronic systems these days are found in pretty much everything. Obviously things like aerospace and automotive and consumer electronics are really obvious ones, but also things like healthcare, industrial equipment, and pretty much every product we use in our day-to-day lives. So ensuring that the systems remain operational, perform as they're intended, is pretty critical to product success and customer satisfaction. So if you're able to properly address electronics reliability concerns, this can help meet the objectives that we have listed above. Typically, customers will try to deal with this by design, build, test, break, and fix, as you can see here, and just kind of keep going through that cycle. That can be quite expensive and time-consuming, especially if your prototype is particularly expensive to build. So design rules and best practices may not provide you with the guidance you need to properly design modern cutting-edge products. By using simulation, specifically ANSYS solutions we're talking about today, virtual models and prototypes can be created and simulated, and this will help you to have a higher degree of confidence that the physical tests you're going to run are going to be successful. As we see here, 73% of product development costs can be spent on test, fail, fix, repeat, which obviously we would hope to avoid for you. So performance, safety and cost are all obviously critical considerations, among others. So devices are required to perform reliably in their intended function in a wide variety of demanding environments. If electronic systems get too hot, if they have mechanical failure, they may not be able to perform at their intended function. In some instances, such as automotive or aerospace, healthcare, many others, this could put people at risk, which obviously we don't want to have. So we just want to help make sure you avoid those challenges. We have a wide variety of customers which have benefited already from ANSYS Electronics reliability solutions. Benefits have typically included those we can see here, such as reduced design and development time, material costs, including fewer board redesigns, reduced product development timelines, improved product performance and reliability. We also have a number of assets such as ANSYS advantage articles, case studies, etc., that can show prospective and existing customers how others have benefited from ANSYS solutions. So if you would like copies of any of those types of things, please just drop a note in the chat. We're happy to share those with you. So engineers have to address a wide variety of design requirements when designing electronic systems. They can range from electrical, such as signal and power integrity, thermal, so the implementation of optimal cooling strategies, or mechanical, such as the ability to withstand thermal cycling, shock, vibration drops. So products are also expected to meet life requirements to ensure they meet their intended function for at least a specified amount of time. No one likes it when their iPhone dies after only a week. Engineers also need to consider the effects of manufacturing, transportation, product operation as part of their design processes. So we try and cover all of these on our webinars that we've been running. As I said, we are on number 4, which is comprehensive multiphysics. The previous 3 are available on demand, and the last one will be available in a couple of weeks. So Ansys do provide a suite of tools and workflow solutions that address a wide range of electronics reliability concerns. And each aspect play a key role in the understanding of how electronic systems operate and perform in a wide variety of applications. So no matter what it is you're making, we should be able to help you. By their nature, electrical devices when in operation generate heat. It's important to not only characterize the electrical behavior of an electronic system, but also determine the thermal effects that arise from its operation. So the deformations of the structure itself, potentially serving as the cause of mechanical failure in PCBs, packages, solder interconnects, and other structural components. So when simulating electronic components, it's important to consider the problem holistically by considering the various multiphysics effects, which is obviously what we're here to learn about today. So in a moment, I am going to hand over to my wonderful colleague, Alex, who's the brains of the operation here. And he's going to be able to talk to you a little bit more in depth about these challenges and how Ansys is uniquely suited to help you overcome them. Over to you, Alex.
Thank you, Laura. Hi, everyone. Yeah, my name's Alex. I'm one of the I'm part of the technical team at Wild Analysis. So I use Ansys on a day-to-day basis as part of consulting projects as well as supporting Ansys customers. So yeah, I'm just going to take you through some of basically the solutions that Ansys have to dealing with thermal reliability and sort of electrochemistry, heat transfer, stress analysis on PCBs and electrical components in general. As I say, if you have any questions during this portion, please feel free to just leave a note in the chat, and we'll get back to it at the end as best I can. So how does Ansys deal with this problem specifically? It's a very complicated problem. That's why I imagine you guys are here to have a look. There's a lot of different physics going on. And basically they all interlink with each other. So it's how does Ansys provide one solution to all this data, one that is reliable enough and is quick enough to be useful as well. So as part of Ansys, simulation is the core business. Ansys are a simulating company. They do this through acquisition as well as developing their own code. Open ecosystem is part of Workbench, which we'll go through in a moment. And they pride themselves on simulation accuracy and being an expert engineering partner to all those we work with. So what does this sort of process look like overall? So you can kind of break it down into like this. This is not extensive. There are multiple other physics that you can sort of get involved in depending on the application. But generally we go from electrical simulation, so using products such as SI wave and HFSS. To look at the power and signal integrity of the board, so looking at EM losses, for example, the heat generation within the board itself. We then pass that to a thermal simulation, or we can do, to work out the flow fields and temperatures, while also accounting for the power and signal integrity from your previous simulation and coupling that with typically a CFD study, a flow study, looking at natural convection away from the board as well. You have to couple these two together. If you have forced convection, natural convection, this will massively impact what kind of temperatures you see in your chips and your boards. Based on the temperature distribution across the boards and chips, you may want to do a mechanical simulation, deformation, stress, shock analysis to see does the board deform under that kind of temperature as well. And then you may want to take this to a reliability analysis. So this is just the kind of the general framework of what you might want to see. You might want to add more stuff in, take more stuff out, model the chips in more detail, for example, which uses a different product. But essentially what we're saying is that Ansys have dedicated products, tried and tested in the industry, that address all of these issues, and they can be coupled together to give you that complete view of your circuit board or your electrical component. So again, what we might see typically as well, not just building up the complexity, but building up the geometry as well. So all of these you can go into as much detail as you would like. So chip and die, you may want to start off modeling the smallest component, effectively the chip and the die. We haven't gone into too much depth into exactly which products, which ANSYS products you may need to simulate these. But again, if you want to know a bit more detail about what specifically you need to address these issues, just get in touch and we'll be able to point you in the right direction. But chips and dies generally come with addressed by a piece of software called Red Hawk. IC package tends to be something called SI wave, and then board assembly can be addressed in multiple ways, like IcePack and Sherlock and stuff like that. So you may want to build up your package step by step until you come to something as large as maybe a data room where you've got the results from all these different systems all linked together to give you the overall impression of what goes on inside your system. Obviously, if you're concerned with board assembly, you may want to just stop at that level, but you can progress that further and further on. Again, we'll go into a little bit, we'll touch on a little bit what a system analysis is and how this can be used more effectively than just a typical sort of 3D model study as well. Okay, so a lot of these do tie in with ANSYS IcePack, as we're seeing here, as sort of your coupling physics. This is your heat transfer physics, what everything seems to need to tie into. But what is the challenge effectively with boards is that everything seems to depend on everything else. The physics are very closely coupled, whether you look at EM losses, heat transfer, deformations and stresses, all of which can impact the other. So it's about coming up with a fully comprehensive multi-physics solution. So this is something that ANSYS provides. We'll look into, we've got a demonstration a little bit later where this might look on the project schematic called Workbench. We'll dip into that a little bit soon, but you can see a lot of these programs can all come together depending on what solution you're interested in and exactly how much depth you want to go into each of these components. So, for example, electrochemical analysis, so just the chip package. So you're looking at, again, Red Hawk, CTA, so your chip thermal analysis, and then therefore you may want to take this data into a CFD study or a system thermal simulation is what it's referred to here. It doesn't have to be CFD, where you can plug this chip in to your assembly, having assessed it in more detail and using those results to give you that system level detail that you might need. But here you can convert between the IC simulation for thermal aware EM, so the Red Hawk or Totem, and you can take that data back and forth from ANSYS IcePack to get a better idea of the environment that it's in as well, which will again inform what results you get on the chip. So it's just a quick example of where this would be quite useful. So about electrothermal analysis specifically, and all the types of analysis you can get. So there are lots of different applications for this. It's not just a blanket, you need to take this from this program to this program, depending on whether you're interested in low frequency, high frequency electromagnetics, or you're looking at voltage maps on PCBs. You may need different types of software, but again, ANSYS do provide all of those. It's just a question of which one do you need at this specific moment in time. Okay. So for example, the bit continued on chip package systems. So this one looks at ANSYS SI wave. So this is the power density on a PCB board. So you can take the power map from your SI wave. We enter the voltages from your different components on the board, some of which you may have analyzed in more detail, and you can use those results as well to inform your density map or your power map. And you pass those to ANSYS IcePack, which calculates the overall thermal map and the temperature distribution across that board, which then you may want to take back into and get a better estimate as to the environment temperatures. And you may do a little bit of iterating between the two before you get an accurate solution. Again, all possible and all available within GUIs as well. So just to demonstrate this fact and sort of what it may look like in ANSYS to set up, Just have a quick demonstration showing you what this looks like in Workbench. So where we tend to start is a product called Sherlock. We go, I think the next webinar in this series is about Sherlock specifically, so I won't go into it in too much detail here. But Sherlock is a reliability tool, but also it can be used as a board file conversion tool as well. So if you have an ECAD model, you can take that into Sherlock, specify all the chips, all the components in that board, and you can export it as a 3D model, which you can then use for further analysis. So if you export it directly, so just showing that there are a few different options in the way you can go about this. Some give you more detail than others. If you don't mind using Sherlock as a standalone program, which you have the flexibility to do, you can export it into Workbench with something that looks a bit like this, where you get the engineering data of all the materials from its extensive database, as well as the 3D CAD geometry, give you a model link into mechanical models, the FEA solver, as well as the IcePack model, the CFD solver. If you wish to use Sherlock within Workbench and keep it all together in one package, maybe you're passing this off to a colleague and you want to do the first section, and that's absolutely fine. Sherlock is available as its own component in Workbench. You simply link all of these components together depending on which physics you're interested in. So this is not an extensive list. This doesn't include any of the electromagnetics capabilities, for example, but these can be added in as well. But for this demonstration, I've just added in Sherlock model, exporting, using Discovery to do a little bit of cleanup, the CAD tool within ANSYS, and exporting that to, first of all, an IcePack model, where you define heat sources, heat sinks, and any convection and the surrounding air. And then that temperature data will feed into the temperature inputs for mechanical. You can have a look at the deformations and the stresses generated within that board for those particular operating conditions. So this is the end result. The results are now, but this is the model. To have a quick look over. It's quite a very basic board just to show as demonstration purposes, but these are the heat producing chips on the top. And then this is out of IcePack's, Sherlock's library, where you have a layer of copper on the top. You then have a layer of FR4, and then you've got a layer of aluminium on the bottom. So you can see here, just a few fixed supports set up, where you may expect some restraints. Maybe it's bolted to the board, maybe it's bolted to a larger assembly or held in place in some way. But we got that total deformation due to a temperature map, which I should have shown first, but there we are. That's imported straight from IcePack, all within Workbench, and it leaves us with this temperature distribution. I did make this chip hotter than this one, so that has come through. You can see that on the bottom there as well. Okay, and then so that variation in temperature leads to a warping of the board. You can see in the cooler areas and where it's restrained as well. So all of this is growing away from those fixed restraints. See, it's got quite a funky shape. However, very low stresses in this particular model. So very low deformations in this particular model, around about 0.1 maximum millimeters. And the stresses around the constraints. So as long as these don't usually exceed the yield strength of the material, it's looking quite good for that particular scenario. You will get some peak stresses around due to meshing and stuff like that. Okay, if anyone has any questions about this demonstration or they just want me to send this to you to have a look around, again, feel free to let us know. So what does this, the overall process look like? So you may do your electrical analysis, take it through to a thermal, and then you see if you're, so I mentioned before, you may do a few iterations between two different pieces of software. This is what this is demonstrating. So your electrical analysis taken through to your thermal. If the two don't tie up perfectly, you may need to do another convergence loop. But again, this is all sorted from within the Workbench window, so this can be done automatically as well. Until you end up with a converged solution, we can then take into mechanical and work out your stresses and deformations. excuse me, where you can work out deformations for the PCB, any solder or any joins that you may have on the board. And you can also you can use sub-modeling techniques to zoom in on areas of interest as well. So I mentioned we'll be touching on some system analysis and how that is useful. So as we mentioned, these very small chips can be analyzed in great detail. If you have hundreds, if not thousands, of these chips, this can be quite a problem to model to model in 3D anyway. So again, ANSYS have solutions for that as well. Some system modeling, which can leverage reduced order models as well. So effectively what it does, use your 3D model to run multiple cases, look at which variables make the differences to an end result, take those and apply them as a system. So instead of modeling in 3D, you're just looking at relationships between certain variables, and you can plug those into a system model so that you effectively have a box component which represents a 3D model without actually running the 3D model. So you can see if you do it properly. So again, ANSYS have ROM builders that you can use. If you do this well, your ROM should behave exactly the same as a 3D model, but should run in a fraction of the time. These can be included in something like products, which can be used for this, so stuff like SCADE and Twin Builder as well. If you want to look at any of those products up. So what does the optimization process look like for systems? So effectively, the overall challenge will be to improve on the design that you already have. If it's not some sort of validation operation, you may look to improve the design of what is quite a complex electronic system. So you start off with parameterize and model setup, looking to define your the equations governing your design. So whether it's you're interested in electromagnetics, whether you're interested in EM losses, natural convection, forced convection, and any boundary conditions, for example, fixed supports. Then take this into a step 3 sensitivity analysis. If you change those variables, how does that affect your study? And then optimization. So how can you come up with a solution there where if you minimize, how can you change those variables so that you get the maximum output from the device that you have? Or at least identify any boundaries that you may occur. Temperature cannot exceed 50 degrees, for example. And how do you come up with a process or a design kit to make sure that doesn't happen? Okay, and just some closing notes really. So these these features deliver high accuracy. There are dedicated tools that have been tried and tested in the field for a number of years that have been acquired by ANSYS over time. They've now been effectively assembled so that they all work together and can export to each other, and you can couple them very, very easily, which effectively allows you to model complex systems completely rather than just looking at certain sections in isolation. You can do it all together. Excuse me. Just take a sip of water. Yes, and then we touched on how a system model may give you certain advantages into if your model becomes large enough in size. You're looking at a data center, for example. You're looking at a full component or control systems and stuff like that, where using a system model may benefit you as well. Okay, well, yes, thanks to everyone for listening. Quite a woman tour and quite a complicated topic, but if you do have any questions, feel free to ask away in the chat. We've got a few minutes left answering your questions. If you do go away and find out you have any questions that you would like to say to us, feel free to get in touch, and we'll get back to you with a good as answer as we can.
Thank you very much.
I'll get back to you, Laura.
No problem. Thanks, Alex. As Alex says, we'll absolutely get back to you if you have any questions that we don't have time for today. If you have anything that's a little bit long-winded, as Alex says, it's quite an in-depth topic. 30 minutes really isn't enough time to cover everything. So please do feel free to ask us so we can come back to you and have a more in-depth discussion offline. I'll just give you guys a couple of minutes to think about it. If you want to pop a question in the chat, likewise, if you're anything like me and you think about the question in about 3 hours time, please do feel free to just reach out to us either by giving us a call or dropping us an email. And we're more than happy to have that discussion with you at a later date. It's no problem at all. So we'll just give you a minute to pop any questions in the chat if you think of them any. You're also very welcome to ask if you've got queries that aren't specifically related to the webinar. If you just have things that you need to get off your chests whilst you're here, we will do our best to answer them. Here we go. Question. Are there any tools to confirm that the assembly will last for 10 years? It's the best one for Alex, I think. So we're looking for durability questions.
Yes, so this is effectively covered by ANSYS Sherlock. So this is covered in a bit more depth in the next webinar. But effectively, what Sherlock is it's a thermal reliability tool. So it's looking at fatigue studies, both thermal and mechanical. So yes, if you want to look at tools that will give you a product life for your electrical components, Sherlock is the place to have a look at and read a bit more up on. But again, Sam, my colleague, will go into that a bit more detail. I think is it next week, the Sherlock webinar?
Week after, I think.
Week after. Okay.
Yeah. Either which way, our wonderful colleague Louise in marketing should be reaching out to you with the dates if you're already registered for this webinar, so you won't miss it.
Sure.
Got 2 minutes